I've discussed a few problems on Compton scattering that I had mentioned earlier, and we have done two videos on Compton scattering. The first part and the second part is an extension into the various forms and as well as the the condition of the unmodified line, that is the Thomson component, that is discussed in the second video. This one has the numerical problems, and to begin with, I've already done them, so I would just be discussing them, going through them. You can take a screenshot or maybe download it to watch later or write them down for your better practice. Now, the first one has asked us to find the fraction of energy of the incident photon that is transferred to the electron which was initially at rest in Compton scattering, and hence we have to show that the photon cannot give all its energy to the electron, which also means that it cannot be observed by it. Now, if you go on to think about it, that the for the second part, what I'm saying is, if the complete energy is transferred into the electron, what would have happened in case of two particles of equal masses? That would have been the case in elastic collision, that we have learned in the higher secondary level 1 physics, that in that case, as an incident particle bearing the same mass as that of the stationary particle on elastic collision transfers entire energy to the second particle, and the second particle then moves on with that energy while the first particle remains at rest. Now, that would have been the case had there been a rest mass of photon, and photon would have had the same mass as that of the electron, but that's not the case, so this is not possible. But mathematically speaking, we can check for that in case we end up with some condition. But as you can see, we haven't. We have just obtained the desired result. The solution carries first value, that is k, that is the kinetic energy of the electron as per the formula that we have earlier deduced, and that has h nu naught times of all of that stuff, which is lambda c, giving the Compton component or the Compton wavelength. And then the kinetic energy of the incident photon is obviously h nu naught, so that when divided to k, that is the kinetic energy of the electron upon the kinetic energy of the photon, as you can see, there's a lambda naught extra term in the denominator, else they would have cancelled out. So with that lambda naught x in excess, this value goes to less than 1. So obviously it gives a fraction. The fraction is what we have obtained, and that fraction is obviously less than 1, which also suggests that the entire energy of the photon hasn't been given out to the electron. For the second part, we have a photon of 3 angstrom of wavelength, the incident photon, that is. It strikes an electron at rest and rebounds at 120 degrees, that is the angle of scattering in this case is 120 degrees, with respect to its original direction. We have to find the speed and the wavelength of the photon after the collision. Now, the difference in length or the wavelength shift that we obtained in Compton scattering is simply the new wavelength minus the old wavelength, the difference in that, and that is equal to h over mec times of 1 minus cos theta. Theta here is the angle of scattering, which is 120 degrees. Cosine of 120 degrees is minus half. Minus of minus half gives us plus half. So we have 1 plus half in the bracketed term. And the lambda 1, therefore, that we have to calculate the new wavelength, because we are supposed to calculate the speed and the wavelength. Well, the new wavelength is equal to the sum of the old wavelength if lambda naught goes to the other side, plus h over mec times of 3 over 2, 1 plus half. So that value, that h over mec, is obtained to be 2.424 times of 10 to the power minus 12, or 2.424 times of 10 to the power minus 2 angstrom units, and that is multiplied to 3 over 2. That gives us 0.03636 in angstrom units, and so we get this value to be equal to 3.03636 0.03636 angstroms, that is the wavelength. While the speed, obviously the speed of the photon cannot be anything less than that in a given medium, in vacuum or air, so it has to be c. So the speed remains unchanged for sure. While the case of the third bit has asked us to obtain the wavelength, or not the wavelength, but the wavelength of the incident photon, that is. We are supposed to calculate the wavelength of the incident photon as well as the energy of the incident photon when the wavelength of an X-ray photon is doubled on being scattered by 90 degrees. Now doubled means that the new wavelength is twice that of the old wavelength. So the difference is obviously going to be equal to that of the old wavelength, because 2 times of old wavelength minus the new wavelength, minus the old wavelength, sorry, is going to give us lambda naught itself. Lambda 1 minus lambda naught. Lambda 1 is 2 lambda naught minus lambda naught is equal to lambda naught, and that is equal to h over mec. We know that value, h over mec, we are familiar with that, we just obtained it. So the thing about trying numericals is that you get familiar with the regular terms and the numbers associated with that. So that is just 2.424 times of 10 to the power minus 12 in meters, and because that is the only thing that we are going to get, because the other term multiplied in brackets 1 minus cosine of 90, cosine of 90 is 0, so we end up with that term only, that is h over mec. So we have obtained that. Now the energy is equal to h times of nu naught, which is equal to c over lambda naught. So as you know that lambda naught was just right before that obtained to be h over mec, so we can substitute h over mec in that lambda naught. The h get cancelled out, mec goes up, so we have mec squared, which roughly comes out to 8.19 times of 10 to the power minus 14 joule. You can calculate that, but I would also suggest you obtain that value in electron volts, because all the energy that is dealt at this level is in electron volts. Now the next part, or the next bit, has the question that with reference to the condition in the previous case where we had the scattering angle to be 90 degrees, calculate the recoil angle, that is phi, if the incident wavelength now is 1 angstrom unit. Now for that we will use the relation between the scattering angle, the recoil angle, and the scattering angle. And as you can see, cotangent of phi is equal to 1 plus alpha times of tangent of theta over 2. Phi is the recoil angle which we wish to determine. So taking the reciprocal of both the sides, what we get is tan phi, or tangent of phi, is equal to 1 plus alpha now goes to the denominator, so that is the reciprocal of that to the power minus 1. Now tangent of theta over 2, now tangent of theta in this case being 90 degrees, theta over 2 is 45 degrees, so tangent of 45 is 1, the reciprocal of that is going to be 1 as well. The term in the bracket has 1 plus alpha. Now alpha is h nu naught times of mec squared, and if you look at it, that the value that we have mentioned or written over there, one of the c's out of that c squared, nu naught over 1 of that c, is simply going to give us a lambda naught in the denominator, and lambda naught is the wavelength of the incident wavelength of the incident photon, which is given to be 1 angstrom unit. So this value over there at the denominator that we see, that is simply 1 angstrom, so we can just cancel it out. So that is what I've done, I've struck out that lambda naught that was there. So lambda naught came in place of nu naught over c, so 1 nu naught and 1 c has gone missing, because there is a lambda naught in the denominator which has a value of 1. Now this is an angstrom unit. Even h over mec that you know of is 2.4424, right? 2.424, and that too comes in angstrom unit, but that is 10 to the power minus 2, as you can see there. I'm just making a small bit of correction over there. This term that you see over there, that is simply H over MEC. Now H over MEC is equal to 2.424 times of 10 to the power minus 12, which means 2.424 times of 10 to the power minus 2 angstrom units. Now this lambda 1 in the denominator, that was in angstrom units, and this comes in 10 to the power minus 2 angstrom units, so they cancel out the angstroms, and what we are left with is this value over here. So this is a correction over there that I must consider. So this is 1, remains as such. 1 is not in any other unit, rather than 1 is just the single 1, no powers of 10 over there. 2.424 with the angstroms cancelled, it simply has 2.424 times of 10 raised to the power minus 2. So this is equal to 1 plus 0.02424, which is the value in the bracket, and the reciprocal of that. So this is simply the reciprocal of 1.02424. And the reciprocal of that is going to be somewhere near 44.3 degrees if you take the tangent inverse of that, because phi is equal to tangent inverse of that term in brackets, and that term in brackets is going to be roughly equal to less than 1, or maybe 0.9 or something. So that goes to be nearly 44.3 degrees, which is approximately, I have taken it as 45. You can keep it as 44.3 degrees for yourself. So that's how we approach this kind of a problem with the values. You can use the trigonometric table for obtaining the tangent inverse, but if given 4 options, you have to, from the multiple choice work, you can easily calculate if it is near about that 45 degree mark. Not greater than 45, but less than 45. Obviously you can select that as an option, as the correct option. The last bit has asked us to calculate the angle of scattering of a 100 kilo electron volt photon so as to achieve a scattered wavelength of 0.138 angstrom. Now with that scattered wavelength, that is lambda 1, we wish to calculate the angle of scattering, which is theta. Now first of all, we have to obtain the incident wavelength from that, so that it gets easier. Now the incident wavelength in that case, if you notice from the energy that has been provided, that is 100 kilos. 100 kilos means 10 to the power 5, and it's an electron volt, so it's better to convert it in joules. So we get 1.6 times of 10 to the power minus 14 joules with the 10 to the power 5 multiplied to it. Now lambda naught is equal to hc over hc over the energy, because energy is equal to hc over lambda naught, so lambda naught cross multiplies, and we get the value over there to be 0.124 angstrom. Now the scattered wavelength has a wavelength of 0.138. So the difference in that case is 0.014, and that is equal to, so we are using the wavelength shift to obtain this scattering angle from that cosine theta term, and the h over MEC, as you know, is 0.02424 angstrom units. So on the left hand side you have an angstrom unit, on the right hand side you have an angstrom unit. They cancel out, and 1 minus cosine theta is simply the ratio of both of those terms, and so we have cosine theta to be equal to that. The numbers are on your screen. So finally we have theta to be cosine inverse of that term that we have over there, is comes out to be, the ratio comes out to be 0.423, which is approximately giving us 64.97 degrees in that cosine inverse. So these are some of the numericals that I tried and shared with you. You can come up with more numericals and share with me, and for enlightening me and others that are associated with this video. Till then, thank you for watching.